would actually, I think, clear all the submissions for one of the written questions, which is kind of what I was worried might be the only solution when I talked about this on Wednesday. And it looks like that is going to be the solution. So there are other ways, like I can kind of download all the raw submissions, and it puts it into like a CSV file, and I can open that, and it's not pretty, but it's still doable. So we were able to mark most of the questions. I do have the TAs helping out, so I think there's just 2 small questions that have to be graded still from that I'm actually not participating in that grading. One of them is just, I think, comparing the queue and the heap in terms of you always have to do a remove min. So one of the, I think, shorter and more easier questions to grade. So I'm hoping we'll be able to wrap it up quite soon, and I can at least post scores. The Connects IT staff did say that, again, when I released the grades, they're not something caused an error when someone was writing the exam. It might have been kind of, there's a whole bunch of possibilities. Like sometimes it happens when people open too many tabs or but the issue is that there might be some sort of, there might be another problem when people try and view their grades, because whatever the person that caused the error, when they try and go back to their quiz to open up their grade, it might actually cause another error, which might make the grade viewing go down again. They're not actually sure if this will happen. So at the very least, I'll be able to post grades on a spreadsheet, and hopefully you'll all be able to view your grades. But if not, if it does end up crashing the quiz tool again, I do have kind of a backup with all the actual data. And if that happens, I'll have to figure out another way to upload so people can kind of see the feedback. I will also post a rubric with my answers and how the questions were graded. But again, it's kind of unsure about a few things right now, just because I can't actually dig into Connects and see what the IT staff is seeing in terms of all the error logs and stuff like that. They have just warned me that this could actually cause a problem later on when we're viewing grades. There's a possibility, but again, I do have all of the raw data, so I can actually like parse through and find each student and find it's all together like in just this random large text file. But I can search through it if it does crash one student. That's something else they might say. It might only crash for the particular student that whatever caused the bug. And again, not that student's fault, just and they might not be able to. So if it is just one person, then I can kind of from the raw data I have, kind of email them their own submissions so they can actually see what they did and then compare that with the rubric I post. Again, I'm hoping and they're hoping that the grading is just going to be the thing that isn't working, and when I release it release it so you can view your submission, everything will be fine. But they did warn me that they're still trying to, I guess they're still doing some debugging, essentially trying to figure out the root cause of the problem and how to reproduce it, and whether or not it'll I guess occur for us. and obviously I'll stay in touch with them, because I just want to make sure that for the final, if we can reproduce this problem and then identify how it occurred, to make sure that if it's a way that I can set up the exam differently, or tell you something about how you open tabs or submit or save, or then that's something I'd like to know. I mean, I have no idea. It could have been just from someone clicking like save too many times in a row, and like it could be just so many things. I know in 110 last fall, someone crashed the assignment submission because I think, again, they just had multiple tabs of Connects open, and they're attaching the file in both and submitted it both at the same time, or clicked them really quickly and didn't know which one was the final submission. There was some sort of race condition there, and that actually crashed all the submissions. So again, there are these little things that the Connect system itself sometimes does have bugs, just like all their software. But again, they were able to identify it and let me know, and we contacted the student, and I think they actually fix it so that can't happen anymore. So yeah, I'm hoping it's the same case this term where we can at least identify what went wrong, so and then therefore be able to solve it and not have that happen again. Yeah, so last fall, I don't even know if I announced it to the class, but at one point when we tried to grade the assignments, it just didn't let us grade them. So I, again, sent an email to the IT staff and yeah, there was this issue, but again, I kind of downloaded all the raw submissions and figured out what the problem was. And again, I didn't even have to announce it to the class because I think they actually fixed the Connect system so people could have multiple tabs when they're submitting something. So again, that was a problem where it was fixed internally, and hopefully that's the case here. Yeah, so in the fall semester, I just emailed the student where they said it was with this submission, and I just asked the student how they submitted or what they did, and kind of just went back and forth with that one student to help figure out and reproduce that error. Okay, so people did say that the quiz went okay. So maybe we can jump to the worksheet then. And so I will say that we've been, a lot of scrolling down to do. We've been doing a lot of kind of just high level conceptual insertion and removal insertion and searching and stuff like that for a couple different types of, I guess, balanced trees. Again, if we think about AVL and red, black, and now 2-3 trees, they're all just the one thing they're doing. And one of the main things they're doing as an extension of binary search trees is just their different ways of creating a balanced search tree. So I was talking with the TAs about next week's lab and about kind of how much we should go if we should kind of start going towards some of the proofs about some of these techniques or implementation about coding this stuff. And again, really just the TAs and myself, and again, the TAs have more recently done interviews. They did say that these are the types of things that they've seen there are common interview questions, and I guess often kind of red-black trees, red-black tree questions can come up on interviews for, I guess, more database-related interviews. Some stuff on B trees might come up. So just thinking about the things that you're supposed to know and would be able to explain in an interview, as well as, so again, just in the lab, you're just gonna make sure conceptually you understand all these things so you can explain the key features of these different types of trees we've been talking about. And then I think at the end, we're going to push our way into some implementation. So I do think it'll be a mix of both in the next week's lab. And in lecture, again, we're gonna try to wrap up trees on Tuesday. And again, just kind of zoom out a bit. We've been kind of really focused on doing these different insertions, but zoom out a bit and kind of think about from a higher level, kind of what the pros and cons of these different things we've been talking about over the past few weeks are. I think at this point, in terms of the previous semesters, I guess it's kind of instructor's choice into how deep you go further into any one of these types of trees. I know, like in a database course, you'll probably revisit B trees and see how so again, these B trees have an M, which is the maximum number of children a tree can have, and a 2-3 tree is just a B tree with M equal to 3, because the maximum any of our nodes have is 3 children. But in databases, often you work with really large M's, like, so each node has references to like 100 other children, just because, again, in that one image I showed, with here, again, if you've got a database where what you want to do, if you're storing your information online or on some web server, you want to really minimize the number of times you have to do that low latency memory access to access all those things. So they want to fill in as many different kind of pointers to where the query is searching for into a single query. So again, they often have nodes full of, I guess this these data blocks full of a whole bunch of nodes, so we can reference a whole bunch of other memory locations and minimize the number of reads. So they're using really short trees that have a high number of, I guess, high number of children nodes per node. And I guess we've talked about this a little bit. I think Carter asked the question when we were doing heaps about, okay, well, what are the pros and cons of having this thing with more children? Again, if you've got a whole bunch of different keys in a node, you do have to kind of search through all those keys, which can take some time. But I guess the idea here is that being able to search through 100 keys is much faster. We can do those 100 operations much faster than it takes to redo another memory access from a web server. So I guess the complexity we're getting into here is now that there's going to be a trade-off with runtime efficiency versus I guess data locality. So where is the actual data stored? And again, if you know that you're able to access all the information you need, and it's, again, not going to be a huge bottleneck going to access that memory, then obviously the one thing you're going to prioritize is runtime. But there are other circumstances where if you can do a lot of number crunching and do a lot of this computation way faster than it takes, and a memory access is millions of times slower than a single one of your computations, then obviously you're going to kind of rethink your strategy. And that's again what the real world is like. And that's why we do kind of talk about all these different sorting algorithms and data structures, which have some similarities in terms of runtime and best case and worst case and average case, but slight differences in terms of stability when we're talking about searching, or in place when we're talking about searching. And again, so when you're working with a system and you've got it's got its own memory requirements or lack thereof. Again, maybe it's got very small onboard memory, so you're gonna have to store everything externally and access it through the web, or maybe it's, again, for some systems now they have a ton of memory, so you don't care about memory at all, and you can just only focus on runtime efficiency. So that's kind of where we're getting to. And because in the real world, it's not just as simple as everything having the same CPU and the same amount of memory, and the memory we know is going to take always at least this much time to access. There's so many different things, and typically when you join a team, they hopefully in that documentation or that specification, you kind of know how and why they're making decisions and what they're prioritizing. But obviously this also isn't often the case, and that's why there's such huge testing teams and QA teams, because they can do these stress tests to see where the bottlenecks are. Does that kind of make sense? Cool. So, I mean, again, on this worksheet, I pulled some stuff from the slides just because it's probably nice to have here, especially when we're doing our first few insertions. So again, the first thing when we're talking about 2-3 trees, so again, we know that all nodes are either 2 nodes or 3 nodes. So a 2 node is just a node that has a key and it's got a left and right child, whereas a 3 node is a node that has kind of 2 keys and 3 children. The other thing that's I guess a key difference with 2-3 trees is that all of our leaf nodes are going to appear on the same level. So we're never going to. So again, in some ways, I guess a 2-3 tree is a self-balancing tree, because whenever we insert, we're going to always insert at the bottom level, and we're actually going to kind of pop things up and make sure that so everything is the same number of levels from the root. And I guess the other idea here is that because now we can have multiple keys in our 3 nodes, we're just going to make sure that the keys within the node are ordered. And I guess typically this is ascending order, but I guess depending on the type of application, maybe you might do something different. But again, kind of since we've been talking about searching, we've kind of been talking about this idea of total order. There's going to be some way we can order our elements, and all of the nodes will have that same ordering. So in terms of a search, again, I didn't do a full example and tracing through a search on the worksheet today, just because I think it's so similar to binary search trees, and we've done a lot of that over the past few weeks because we've been doing how to do that with insertions to binary search trees, AVL trees, and red-black trees. So again, this is the exact same as a binary search tree where, again, if we're looking at a node we want and we want a smaller value, we're going to go left. If we're looking at a node and we want to kind of find a higher value, we're going to go right. The only difference here is with 3 nodes, we kind of just apply that rule how you'd expect if there was an extra key. So if it's smaller than both keys, we're going to go left. If it's between the keys, we're going to go down the middle to the middle child. And if it's larger than both keys, we're going to go to the right. So I think, again, to me, this is fairly intuitive as in terms of how I'd expect this to work. So again, we're just we're comparing it against the keys, and we know that all the lower values are going to be in the left subtree. All the values between those 2 keys are going to be in the middle subtree, and all the values greater than those keys are going to be in the right subtree. Any questions about this? Let me know. I mean, to me, this does seem kind of how this search works seems fairly intuitive, but certainly if you have questions, let me know and we can talk about it. Because it might also just seem intuitive to me just because I've been working with these tree-like structures for quite a bit longer. Okay. Doesn't seem like there's questions. Okay, so for an insertion, we're first going to, again, apply our search to figure out which leaf node to insert it into. So we're going to kind of start at the root, and if the root is a leaf node, then we're going to insert it there. But if not, we're going to say, okay, which direction from the root should I go? Should I go down the left or to the right or the middle if it's a 3 node? And eventually we're going to kind of go left and right through our tree until we find a leaf node. And that, when we get to a leaf node, that's where we're going to insert this element. The idea here is that if we insert a 3rd key into a 3 node, because again, 3 nodes already have 2 keys and they go in 3 different directions from there. But if I insert a 3rd key into a 3 node, it's going to overflow. It's going to have too many keys now. So what we're going to do is we're going to split it, and the left value is going to go to the right value is going to go to the middle. And I guess if there's something in the middle here, or can't with its A and B, it's going to go up. And I think the best way to see this is actually when we actually start working through some of these examples. But I'll keep this over here and reference these instruction steps as we go, because we will see a lot of this. And the thing I want to make sure that we cover today was also that this is actually can occur more than once. So when we insert the middle node up, that could actually cause a secondary overflow. And so when we go back to step 3, we might actually see there's a second overflow and causing us to do that same split again. I did a little bit of this in the videos, but not a lot. And so I tried to kind of get you to think about it a little bit with the quiz. But it seemed like, that went okay. I know I did see for some of you, it took a few attempts, but it looks like most of you ended up getting there quite soon or quite quickly. So how did I do this last day? I think I did like maybe insert in blue, but it doesn't really matter. So we're going to insert a 41 to begin. And we know that the 41 is just going to be this node here. Then what we'll do is we will insert a 32. And so we've already got a 41. And all we're going to do is insert a 32. Again, because we're at a root node or a leaf node, we're going to insert it into this node. Where anytime we visit a leaf node, we're going to insert it into that node. So we've got a 32 that we just inserted it, and there was already a 41 in this place. And I guess I can kind of do it like this. I'm not sure the best way to draw these. Next thing we'll do is insert a 6. So when we insert the 6, we've got this node, this 3 node now, that has 32 and 41 in it. Now we're inserting a 6. So this is a problem. This is an overflow. So if the node overflows, again, as I've got in the bottom right here, or left here, it now contains 3 keys, we're going to split the node. So what I'll say is we're going to split it. So we're going to kind of cut it here and here. I'll say, and the 32 is going to go up. and these are going to go to each side. So what this is going to look like is we're now going to have the 32 as the root. The 6 is to its right, and the 41 is to its, or sorry, the 6 to its left, and the 41 is to its right. Does that make sense? Oh, what did I do? Any questions about how I did that split? Okay, so we've done the 41, the 32, and the 6. The rest is just the node I'm inserting at that step. Yeah, just so we can see what the new node is. You don't have to do it. I'm just doing it just so you can see the differences from the old tree. So now in the old tree, we had all these values. 32 went to 6, went to 41. And now the new node I'm inserting here is the 80. And again, we know, 80 is going to go right from 32, and then it's going to go right from 32. Then we're going to be at a leaf node, so we're going to insert it here. Oh yeah, no, sorry. I just I guess I did start that with red black. No, more just to keep track of the actual thing I'm inserting in this step. Just because I know when they get bigger, it's hard to see, wait, where did I actually insert this thing? No, sorry. I can do it. Would you prefer I just do it all in black? I can do that if you want. Okay. Oh. Okay, so we can, now we'll insert a 66. I'm going to do it here just because I know I'm going to have to do a split, because again, I know I've got this is the tree I've got right now. And if I insert 66, I know I'm going to go right from 32. Now that I'm at a leaf node here. So I'm at a leaf node that has 41 and 80. And this is where I'm going to put that 66. But what we've got here is now we have to split this and bring the 66 up. Or I guess when I say up, I mean up. So what that's going to look like is we're now going to have 32. We're going to have 32 here. Oh, sorry, 32 and 66 here. To the left is going to go 6. And now because we split these two nodes out, I should have done this splitting left and right. Split left and right. We know that the 6 is going to be the left child of all this. 6 is going to be the left child of all this. In between the 32 and the 66 is going to be the 41. And to the right is going to be the 80. Does that make sense? So again, we split the 41 so it went left, the 80 so it went right, and the 66, that again, we know that 66 is always going to be between those two. It went up. So again, we've still kind of got the 66 between those two. So this is how, I guess, the binary search tree property is still maintained. Any questions about this? So this is like the first time we actually had to split, and I guess when we split, we went up and made a 3 node. We'll get the root overflowing in a second, but again, it's going to be the same process. Again, we're just going to follow this pattern down in the bottom left corner, and the same thing that happened here, where we're just going to have, if the root overflows, we're going to go up, and we're going to have a 3-level tree, or I guess a tree with 3 different levels, that where the middle value from the root, or the middle value from the current root, when it goes up, it's going to now be it's going to be a 2 node, and it's going to be the only key in our new root. So we inserted 66. I'm worried I'm going to run out of space, so maybe I'll do another insertion here. Insert 43. So to insert 43, we know we've got this 32. We know we've got this 32 and this 66, and they're the root right now. And from the left of 32, we've got a 6. In between them, we've got a 41. What are we inserting? 40. We're inserting a 43. And to the right, we've got an 80. And now we know that we're going to go, 43 is between 32 and 66. We're going to go down the middle to the middle child. And we found a root, we found a leaf node, the 41. So we're going to put it right in here, 43. And again, we don't have to split anything because that's still, it's still a valid tree node. So we've done that one. 25 is going to be pretty easy as well. 25, 50 is not. Okay. So maybe I'll also insert 25 into this one now as well. So inserting 25, what we're going to do is we're going to go left from the root, and we're going to see, okay, I can actually put it inside here. Which is, again, I'm adding to a node, but I'm not overflowing it yet. But now, when we want to insert a 50, where we've got this 32 and a 66, and to the left we've got 6 and 25. Between that, we have a 41 and a 43. And to the right, we have an 80. But now, again, we know that 50 is going to be between 32 and 30 and 66. So I'm going to want to insert it. I'm going to want to go, I guess, down the middle to the middle child, which is a leaf node. So I'm going to try and insert the 50 here. And obviously, we're going to see that we need to do a split. And this is going to answer Kevin's question now. So again, 43 is going to go up to the parent. 41 and 50 are going to split off to the left, which is going to get us this 32. 32, 50, and, oh, sorry, the 43 went up. The 43 goes up, 32, 43, and 66 up here. Then we had 6 and 25 over here. But now, as Yeah, so we always going to insert it at a leaf node. So the question was, why didn't I insert it in the middle? So we're always going to insert it at a leaf node. And then if we overflow a leaf node, then we're going to, I guess, kind of do this split where the left goes to the left, the right goes to the right, and the middle goes up. So the middle went up. This 43 went up here. And we're just kind of now just doing an insertion to this other node here, which is the only time we'll only ever insert into a non-leaf node when we have that split that pushes a node up. Yeah, exactly. So we're always going to insert at the bottom level. But now, when I move this 43 up, we see that again we're going to have to do another split and have these go to the left and right. So what that's going to look like, am I going to fit this? What that's going to look like, I guess I can. Okay. What that's going to look like down here is we're going to have the 43, whoops, is now the root. It goes left to the 32, goes right to the 66, because again, 32 went left, 66 went right. And then again, we still got our 6 and our 25 down here. We've still got the 41 was kind of, again, the right, but it went right from the 32 before. It's still going to do that. The 50 went left from the 66. It's still going to do that. And the 80 went right. So we've still got this exact same ordering, which will allow our search to work. So this was a hard one. So maybe I'll see if people have questions about this. So again, we always insert to a leaf, which we inserted right here. Then we had to split it. So the 41 went to the left, the 50 went to the right, and the 43 went up. Then we had to do the same thing where the 32 went to the left, the 66 went to the right, and the 43 went up. So splits on the middle children are different. Always, every split's always going to be with when we have 3 keys in a node, always the outsides are going to go to the outside and the middle one's going to go up. And I guess so the ones that go to the outside are going to be the left and right children of the one that goes up. And they're still going to have the same pointers down from them. So again, the ones that go left and right, 32 is still going to have this same subtree below it. Same with 66. But the one that goes up, its left and right child are going to be those ones that went left and right. Did this just answer your question, Ming Sheng? Because again, 32 all already went right. There was already this connection here, right from 32 to 41, and that's going to be the same. Okay, cool. Yeah, so the outside nodes still kind of keep the thing, the references that go left and right from them, but it's the parent node that gets is kind of its own new node, and it gets left and right child, which are those two being the two nodes that split left and right. So I think inserting 72 in this is actually not going to be too bad at all. We're inserting 72. So again, from the parent, if we're going to insert 72, we're going to go right, right. Then we're in a leaf node here. So we're going to put it in right here, and that's fine. We don't have to do any work. So again, we're always just starting at the root and saying, and determining which direction to go. I guess we're always going to assume that we've got unique keys, figuring out which direction to go. And then if we ever get to a root node where it doesn't have a left and doesn't have any children, they're all null, then we can put it into that node. Any questions? Okay, we can jump to the next page. The next page has some, I guess, just more complicated examples. When we actually have to kind of do multiple splits and chain them up, we've kind of seen that we had to do one chain right, I guess here we had to do a chain, or we did two splits, but we're actually going to, on the next page, actually do, I think, one with three splits at least. But we can, if there's no questions, I'll scroll down there. We got 10 minutes. Okay. Wonder if with the time left, we should just skip to the right side and do the most complicated one. Why don't we jump to the most complicated one? And if we have time, we can go to the left side. But we'll do. Why don't we do this one just so I make sure we have time to do it during class? I'll obviously post a solution with both. Yeah, so we'll just focus on this one for now. So again, what we want to do is we want to insert a 15. So we're going to start at the root. We know we have to go left. Then we're going to go right, and now we're in a root node. So we're gonna insert it right there. So what we're going to have so we've got here is now we had a 17 and an 18. And we're going to put the 15 in here now as well, which is obviously going to cause a split. 15 is going to go left, 18 is going to go right, 17 is going to go up. So all that's going to happen here is we're just going to have, and I might not draw the whole tree, because the whole middle and left side is going to stay the same, but we're going to have a 12 and a 15 here. And the 15 is going to go right to 18. Oh, sorry, it's going to be 17. Sorry, the middle one goes up. The middle one goes up. The 15 is going to be here. And the 12 is still going to go left to 3 and 6. And the rest of this is all going to be the same. So we only really affected just this left side of the tree here. So in here, it's still going to be the 32 and the 41, which is going to, et cetera, et cetera. But now that we've got this tree here, and we want to, so again, this was our insert of 15. Now if we want to insert a 2 into this tree, we know what we're going to do is we're going to start at the top, we're going to go left, we're going to go left, and now we found a leaf node. So we're going to insert it right here. So what's going to happen is we know we've got a 12 and a 17 here. That's all going to be the same. But now what we have here is, again, we know that we are going right to the 18, middle to the 15, and we've now got we've now got 2, 3, and 6 in this node over here. So again, what we're going to need to do here is split it. 6 is going to go right, 2 is going to go left, 3 is going to go up, which if we think about this is now going to give us a 3, 12, 17 parent node. And again, we're still going to have the 2 here, the 6 here, the 15 here, and the 18 here. But now again, we've got this parent node needs to be split as well. So the 3 is going to go left, the 17 is going to go right, and the 12 is going to go up. Which in turn is now going to make it so our root node is 12, 21, 43. With 12 going way left over to 3, then the 17, then the 32, 41, then the 66. So we've got to do another split. And then this is all the same down here now. So now we've got to split this again. So we're going to make an even higher, one extra level in our tree. But again, those same rules apply. So what we're going to do here is, split it so we've got a new root, 21. '21 is going to go left to, the 12 went left, the 12, and the 43 went right. But we're going to make sure we maintain all of their subtrees. So again, this subtree should still remain intact. This subtree should still remain intact, et cetera, et cetera. So what's going to happen is 12 is going to go left to 3, which is going to go left to 2, and right to 6. 12 is going to go right to 17, which is going to go left to 15, and right to 18. 43, So 43's left tree was this 32 and 41. I don't think any of this stuff's changed, 39, 40. So I'm just looking up above it now. And over here was the 66. And that's going to be our final tree. So the thing is we added one thing, and we actually had to do, what did we do here? We did 1 split, 2 split, 3 splits. But we see that our binary search tree order still works. So again, if we want to find like a 42, we're going to go right, left, right. Let's use a middle path. I guess if we wanted to find like 35, we'd go right, left, middle, and see, okay, it's not here. So in terms of being able to do this, would you be able to do this kind of this insertion, I guess, finding the insertion spot and then doing a split and figuring out how to make the leftmost node go left, the rightmost node go right, the parent go up and point to those as its new children? And I guess also be able to do this with a chain reaction of splits. I'll do the poll for just a couple more seconds here. I know people are probably also still writing. I maybe 5 more seconds for the poll. 4, 3, 2, 1. So yeah, it looks like, again, most of you are confident, which I think is good, because I think this thing is, once you get the hang of it for both B trees, 2-3 trees, red black trees, AVL trees, all those things, once you kind of understand how the rotations work or how the splits work or how these things work, it's not too bad. But I think before understanding those each one of them has a few very specific rules. Without seeing those rules, if you just see, wait, how did we go from this tree right here to this tree right here? It's really hard to kind of figure out, wait, how did this new node get all the way to the root, or how did this rotation happen where this whole tree is restructured? And again, with AVL trees and our red black trees, when there's like the adoption of the parent for those certain rotations, I think it can be really hard to kind of reverse engineer these things. So I do think, again, once you understand the things to look out for and how to, I guess, fix those issues. So with the AVL tree, it's an imbalance. With the red black tree, it's the 2 reds in a row with, and depending on the parents' siblings color, whether or not you have to do a recoloring or a rebalance. And then for the 2-3 trees here, when we overflow a node, again, the things to look for, and then how to actually solve those problems. Again, with whether it's a rotation, a recoloring, or a split and kind of like a bubble up. So again, what we'll do on Tuesday is probably not any more kind of worksheets of just how these operations work. Maybe kind of try and wrap up this whole kind of thing on different tree structures with a little bit of a zoom out a little bit and just kind of, again, be able to compare and contrast some things. And then the lab, you'll get a little bit more practice with some of the operations. And again, then we're going to shift into either some implementation and or some proofs. And the next assignment will probably be released on Monday as well. Any questions? Yeah, good question. I've been looking into removal a little bit. I was looking at it just this morning before class, and as far as the past few semesters of 225 that I have access to, they've never really done it. I'm not sure why, because we certainly did removal for AVL trees. I will. I'm going to email Rich, who often does this course and does 226, and ask why. I'm not sure if it's because maybe that's something that's pushed back to 226, the second half of this course, or not. I know the last time we talked, he kind of said, okay, don't do this because it's going to be covered then. So trying to kind of, because these two courses are kind of one after another, some things are kind of pushed back. So I'll ask him about it, and we'll see. So we might do it, and or maybe it'll just be kind of a thing that I put in videos. But we'll see what happens when I hear back from Rich. I think you're gonna do some. I guess it's kind of up to the TAs. I often have ideas for the labs, and I talked to the senior lab instructor David. So I talked with them yesterday about my plan for the labs and give an outline. But it's up to them. I give them a little bit of freedom because again they've done these courses recently too, and they know again some of the challenges that they face, and so I give them some freedom to be a little bit flexible there. So it might be Java code, it might be pseudocode, depending on what they think is will be the most useful. Any last questions? Okay. So yeah, if you don't do a lot of coding in the lab, I might add a little bit to the assignment. So we'll see. We'll definitely make sure. I really just want to make sure after I talk with Rich that we've covered topics and we've reached the learning objectives that you need to know and are expected to know for 226, just to make again, if this kind of larger class on data structures and algorithms has been split up into two classes, I just want to make sure that between the two classes you're getting everything you need. And again, if I'm spending time doing something that you're going to see again in 226, then it would probably be better that we shift to another topic that you're not going to see again. So I just want to make sure that we're hitting all the topics that we need to, so that complete picture across 225 and 226 is complete. So yeah, I'll talk to Rich and we'll go from there. I think the next two are both going to be kind of out on Monday and due the following Monday. So again, we're going to have one out on the 13th, due on the 20th, and then one on the 20th, due on the 27th, and then our final will be on the 31st. Yeah. Any last questions? Okay, have a good weekend then. I do have office hours for the next 2 hours. Yeah, feel free to jump over to that Zoom call if you want to talk about some of this tree stuff we've been doing, whether it's AVL trees or red-black trees or 2-3 trees. I'd be happy to chat about it. If not, have a good weekend, and we'll see you on Tuesday.